This is the video notes for Unit 6, Lesson 2, Is It Right? This is a Solidify Understanding lesson, and it starts off with a jump start. In the jump start, we are creating and classifying different kind of triangles so that we can easily build triangles on a grid if we need to, which we will for later on in the lesson. So I have actually added a little diagram to help us classify triangles. You can classify triangles two ways. You can classify them by side or by angle. If you classify by side, then your options are an equilateral triangle, an isosceles triangle, a scalene triangle. If you classify by angle, you can call them an acute triangle, a right triangle, or an obtuse triangle. So that's how we're going to classify once we build the triangles. For the first problem in the jump start, it has us add a vertex at 2, 4. So let's put that on the graph. So that ends up right here. And we'll go ahead and connect our lines. And then we have to decide what kind of triangle that is. So it looks as if it is obtuse, because of that large angle right there that looks bigger than 90, and it looks like it is scalene. So we'll add those descriptor words for question 1. Obtuse and scalene. I'm going to go ahead and erase what I did on the graph so that we can move on to question 2. So I need to select a little drawing that I did. There we go. Okay, so in question 2, it has us put the third vertex at 2, 2. So let's go ahead and do that. And then we'll connect those two. So let's look at our little diagram. What kind of triangle did we just create? To me, it looks like a right triangle, and looks like 2 of the sides are equal. So that would be isosceles. Okay, so we would name this one right and isosceles. Okay, let's move on to number 3. So number 3, we put our point at 0, 0. So let's put it there, and then we'll extend our lines. This one looks like it would be acute. This angle C here is less than 90. So let's write acute. And it does look like 2 of the sides are equal, like those 2 are equal. So I'm going to call that acute and isosceles. Okay, let's move on to number 4. So in number 4, we put our point at 6, 6, which is over here. So that'll be our new C. And that one definitely looks like a right triangle. And these 2 sides look equal to me, so that'll be isosceles again. Okay. All right, let's go ahead and do our last 2. Okay, so 5, we put C at 3, 2, so right here. So that is our new triangle. That looks like an obtuse angle right there. So we'll say obtuse. And none of those sides look equal, so that'll be scalene. Okay. Our last one looks like has the point at 1, 2. Okay, so let's put our point there, 1, 2, so right here. So that looks like acute and scalene. So none of the sides are equal there. So we'll say we just created an acute scalene. Okay, so this skill that we just did should help us as we are creating triangles during our lesson. We're going to go through a launch next. In the launch, it kind of gives us some additional notation and some basic ideas about lines that will help us with the concepts today. So in our last lesson, we talked about parallel and we also talked about perpendicular. So our first task that we're going to do is look at this big graph, and we're going to try to identify any lines that we think are parallel to each other. Now initially this is just going to be kind of our gut reaction. So I think that this one and this one and this one are parallel. And as we go through and identify, I'll teach you how to name lines or remind you. So we name them based on the points located on them. For example, on this top line that I've highlighted in blue, we have E and F. So I can actually call it line EF. So I say line EF. And to show that it's a line that goes on forever in both directions, we're actually going to put a little line above it with arrowheads both sides. So I think line EF and line DG and line BO, I think those are parallel to each other. Okay, and I'll tell you why I think that in a moment. But let's identify any others that we might think are parallel. So I'm thinking that these two are also parallel. Okay, I'll name them using points on the line. So I'm thinking that line AB and line IH are parallel. Okay, now the reason why I think that they're parallel, other than like they just look it, is having to do with their slopes. So if I look at the slopes of the blue lines, so I'm going to zoom over there to the blue lines and kind of see what their slopes are. It looks like this bottom blue line goes down 1, right 2, so -1/2. And then so does the middle blue line, -1/2. And then so does the top blue line, -1/2. So what we're noticing is they all have the same slope. And so that could be our proof that they are parallel. They're going to run alongside each other forever, never touching. Let's look at the slopes of the red lines. So for the red lines, looks like I've got a slope of 1/3, so up 1, right 3, and the same thing happens on the top red line, a slope of 1/3. Okay, so I think that's sufficient proof that we've chosen wisely, and that the sets of lines that are parallel to each other are indeed parallel to each other because they have the same slopes. Same slopes. Okay, so right here we've learned two things. We've learned that parallel lines have the same slopes, and we've also learned a notation for writing the name of a line. We use 2 letters on it, and then if it's a line that goes on forever in both directions, we do a line above with arrowheads. Okay. All right. On the next page, we actually learn a symbol to help us write the word parallel if we don't want to write that word. So this will be really helpful if, just for shorthand. So we can state the idea that 2 lines are parallel symbolically by writing this. We can say line AB is parallel to line CD. This is an example. So these railroad track kind of symbols mean the word parallel, is parallel to. So that's a great shorthand for writing parallel. Okay. Now we're going to move on to the idea of perpendicular. So parallel, we've got down, they have the same slope, they'll never cross. We have a notation for it. Now the idea of perpendicular, we're going to start talking about by just stating a fundamental idea. So this is something that we believe, we know it's true, and I want you to circle or highlight or somehow underline it. This is really huge right here. The fundamental idea is that horizontal and vertical lines are perpendicular to each other and form 4 right angles. So if I have a horizontal line and a vertical line, I know they form 4 right angles, which is what it means to be perpendicular to each other. Let's look at this grid and show an example. I have the horizontal line y equals 2. So let's write that on our graph. And then I have the vertical line x equals 3. So let's graph that. So just by this fundamental idea that we highlighted here to the left and we circled, we know that y equals 2 and x equals 3 are perpendicular. And right here, where they cross, we've got 4 right angles forming. So right there is one, right here is one, right here is one, and right here is one. So that is really important to pay attention to as we talk about perpendicular lines. Now this is true for horizontal and vertical lines, but what if we don't have horizontal and vertical lines? What if they are turned at an angle? How do we decide if lines are perpendicular to each other? So it has to do with the slope. Okay, so we're going to do a few experiments now to make observations about the slope and how it changes when we have a perpendicular line situation. So let's go ahead and do our first experiment. So our first experiment gives us a line segment, AB. A starts at 2, 3, and B starts at 4, 7. And the first thing that they want us to do is find the slope of AB. So I'm going to go ahead and do that. It looks like it goes up 4 boxes and right 2. So that's going to be our slope. So I'll fill that in over here. So the slope of AB. And you'll notice I didn't do the arrowheads above AB this time, and that's because the line does not go on forever in both directions. This is just a line segment, so this is a new notation here I want you to pay attention to. So the slope of line segment AB is up 4, right 2, which is the same as like 2 over 1, which is just 2, okay? Now they want us to locate and name a third point so that A, B, and C form the vertices of a right triangle. So this is why we did the jump start, so that we can be comfortable drawing in right triangles on a grid. And they want AB to be the hypotenuse, the longest side. So I think I'm gonna put my third point right here, and that will be C. And that's gonna be at 4, 3. That's the one I've chosen. So C will be at 4, 3. Okay. Now, how do I know that the triangle that I just created forms, is actually a right triangle? So we look at it, and we just read a fundamental idea about right angles, right? About perpendicular lines. We just read on page 15 that horizontal and vertical lines are perpendicular, and we just created a horizontal and vertical line. So that's enough proof to me that we've created the right triangle correctly, because line segment AC is horizontal. So AC is horizontal, and line segment BC is vertical. And because we constructed it that way, we know that this is a right angle. So forms a right angle. Okay. Now what they want us to do is they want us to rotate the right triangle 90 degrees clockwise about point A and explain how we know that we rotated it correctly. So let's go over here and we're going to do a 90 rotation counterclockwise. So we're going to the left. So if line AC is 2 boxes long and it's horizontal, in order to rotate it around A 90 degrees, it's actually going to be 2 boxes long and vertical. So this is going to be our new location for C. I'm going to call it C prime. Right there. Now if BC is 4 boxes long and vertical, in order for me to rotate it 90 degrees, I'm going to end up having it be 4 boxes long and horizontal. So B prime ends up being over there. Let's go ahead and connect it. This is our rotated right triangle. Now, as I was building that, I shared why I think I rotated correctly, and that's actually the next question on the experiment. How do I know that triangle A, B prime, C prime is a right triangle and rotated correctly? Well, it's because the legs of the triangle switched from being horizontal to vertical and vice versa. So A, C prime line segment is now vertical. And B prime, C prime line segment is now horizontal. Okay. Now our very last thing we want to do in this experiment is to compare our slopes. So originally, the slope of AB was 4 over 2 or 2 over 1, or just 2. I'm going to use that 2 over 1 because that'll help me do a comparison. And then let's go ahead and find the new slope. So the new slope will be for a B prime. Okay, and then I'm going to go up there and look at it. So what is our new slope? So it looks like our new slope is down 1, right 2. Down 1, right 2. So that's negative 1/2. Okay. And then now we make observations. What are we seeing about the slopes? The first thing that I'm seeing is that the fractions are flipped. Okay, so that'll be my first observation. Flipped. And I'm also seeing that one of the slopes is positive and the other one is now negative. Okay, so flipped and opposite signs. All right, so let's see if we see this pattern again, because that'll help us come up with a rule for the slopes of perpendicular lines. So let's do one more experiment. All right, here we are, experiment 2. This is task 3. So we're going to go through the same process. We're going to find the slope of the original line. So this one looks like it's 1/3. So M equals 1/3. Because it goes from A to B, it goes up 1, right 3. And then we need to locate the third point to create a right triangle. So I think my third point is good right here. So that'll be C at 5, 3. So C is at 5, 3. And then they want us to explain how we know the triangle that we formed is actually a right triangle. And it goes back to that fundamental idea that a horizontal and vertical line form right angles and are perpendicular. So let's list the sides that are horizontal. So AC is horizontal and BC is vertical. Okay, so that proves we built our right triangle correctly. Now we're going to rotate and explain how we know we rotated correctly. So I'm going to go ahead and focus on the graph. So we're rotating about point A, 90 degrees counterclockwise. So line segment AC is 3 boxes long. Instead of being flat, horizontal, it's going to be standing up. It's going to be vertical. So I think that C prime will end up here. And then BC is just 1 box long. It was vertical, now it's going to be horizontal over here. Okay, so that's B prime. So this is our new triangle. Okay, so let's add in our explanation saying why we know we rotated correctly. So we know that AC prime is now vertical, and it's the same length, just vertical. And we know that B prime, C prime line segment is now horizontal. Okay. Now our last job is to compare the slopes. And this is what we're trying to get to. We're trying to get to a result that keeps on repeating, keeps on getting the same result, so we can prove our observations about the slopes of perpendicular lines. So our initial slope for AB was 1/3. Okay, so I'm going to say AB slope was 1/3, and then AB prime slope. Okay, and I'm gonna go up to the graph and zoom in and see if I can find the slope. It looks like that slope is down 3, right 1. Very interesting. I think this is the same pattern that we found for the other one. Do you see that they're flipped and one of them has the opposite sign? So I'm going to teach you a vocab term right now. So when you see this happening, when slopes have the fraction flipped and have opposite signs, they're called opposite reciprocals. So write that vocab term in your notes, please. Opposite reciprocals. Okay, so that is the idea of flipped slopes, and one is positive, one is negative. So I think at this point we've got 2 experiments that showed the same thing. I think we're actually going to skip the next 2 experiments. So if you would like to cross out number 4, you are welcome to. And then cross out task 5, you're welcome to. They're just going to prove the same thing. We're going to go now to our conclusions, and then we'll do our takeaways. Okay, so our first conclusion, task 6 on page 20, says, based on experiments 1 through 4, state an observation about the slopes of perpendicular lines. Okay, so this is kind of our, what we're noticing. So I'm going to say that perpendicular lines have opposite reciprocal slopes. Perpendicular lines have opposite reciprocal slopes. Okay, and while we only did 2 experiments to show that this is happening, the argument that we could use to justify why this is always true has to do with how the legs on the triangle were switching as we rotated. So that will be kind of our proof right here. Since like the legs are the two shorter sides of the triangle. Since the legs switch as you rotate the triangle, it makes sense that the rise and run for the slopes switch to. Okay, because we're making, as we rotated, like the horizontal leg became vertical and the vertical leg became horizontal. So it definitely makes sense that the rise and the run for the slope would also switch as we are rotating the triangle. Okay, we're going to learn a shorthand notation for perpendicular next. So if two lines are perpendicular, we can actually do a shorthand just like we did for parallel. We did the kind of railroad tracks. We can say that line segment AB is perpendicular. So we do like this upside down T symbol to line segment, let's just say CD, just to choose two random line segments. Okay, let's go ahead and go to our takeaways. So our takeaways just kind of have us finish summarizing what we're noticing. So when working with lines on a coordinate grid, I know the lines are parallel if there are three scenarios possible that could happen. So if the first scenario is if they have the same slope, okay, so that's the first scenario, or are both vertical, okay, and then the third scenario is or are both horizontal. Okay, so I'll show you in three little pictures what I mean by that for those three scenarios. So the first scenario, they have the same slope. Okay, so that looks like this little picture. So I have two lines. The slope on my first line is, let's say it's 1/2, and the slope on my second line is 1/2. Okay, definitely parallel. Now the second scenario is if they're both vertical. So if you can imagine two vertical lines, yes, those are parallel. And then the third scenario is both horizontal. So two horizontal lines. Okay. Then what about perpendicular lines? So I know the lines are perpendicular if. For perpendicular lines, we've got two scenarios that could happen. So I know the lines are perpendicular if they have opposite reciprocal slopes. So that's the first scenario. They have opposite reciprocal slopes. Or there's one other scenario, or one line is vertical and the other is horizontal. Or one line is vertical and the other horizontal. Okay, so I'll show you what that looks like by doing two drawings. Okay, so the first scenario is they have opposite reciprocal slopes. So that looks like this. let's say I have a line and its slope is -2/1. And then I have another line and its slope is +1/2. So those are definitely perpendicular. And then the second scenario is I have one vertical line and one horizontal line. Those are definitely perpendicular. That was the fundamental idea. Okay. So those are our takeaways. We have 3 vocabulary that we want to fill in really fast, just so that you're really clear on what a point is, because we use that a lot, but we don't often understand exactly what it is. So unlike a dot actually has a size to it. You can enlarge the size of your dot or shrink it. A point is just a location. So unlike a dot, a point is a location with no size. With no size. So if I say point A is at 2, 2, it's just the point at that spot. Okay, it doesn't have any size. Okay, and then our second one is unlike a stroke of ink that has width, a line has no width. It's only one dimensional. Has no width. It is one dimensional. Okay. And then our last vocab is a plane, which is unlike a piece of paper, and a piece of paper actually has thickness. A plane on a coordinate grid has no thickness. Has no thickness. It is two-dimensional. Okay, and I'm just going to draw a quick picture to show you what I mean by each of these. So let's say I have this coordinate grid and I want to draw a point. There's my point. It is just a location. It has no size to it. It's just that spot. Okay, now if I want to do a line, I have 2 points that are connected. Now that line has no width to it, right? It's just one dimensional. It goes from this point to this point. Okay, now a plane is when I connect 3 or more points. So that's the plane right here. It is two-dimensional. It has no thickness to it, but it is considered a plane on your coordinate grid. Okay. So I hoped that this made sense, and I wish you best of luck on your practice.